Welcome to the Explainer. If you're currently tackling Cambridge AS and A-level Mathematics 9709, you've probably felt like differential equations is a bit of a maze. But what if I told you there's a way out? What if you had the exact playbook, the actual cheat codes that the examiners use to grade your papers? Well, today we're pulling back the curtain on topic 3.8, differential equations. We're going to decode exactly how to level up your answers so you can secure those top marks. And right off the bat, you have to understand the sheer weight of this topic. Topic 3.8 accounts for a massive 15% of your total exam marks. Think about that for a second. That is a huge chunk of your final grade wrapped up in just this one conceptual area. So honestly, you simply cannot afford to gloss over this. Mastering separating variables, it isn't just about getting one or two questions right. It's absolutely crucial for securing a foundational pillar of your entire Mathematics 9709 score. So to secure those marks, we need to shift your mindset from being a passive test taker to becoming a highly active exam strategist. Here is our playbook for today. 1. Core principles. 2. The methodology. 3. The method mark strategy. 4. Top examiner warnings. And finally, 5. The final evaluation. Okay, let's jump right into Section 1, Core Principles, or the theoretical foundations. Believe it or not, Cambridge isn't just testing your ability to mindlessly move numbers around a piece of paper. The assessment framework heavily prioritizes deep analytical depth. The examiners actually want to see a connected conceptual understanding from you. They're trying to figure out if you can take established principles, like your basic rules of integration, and apply them to some real-world scenario that you have literally never seen before. It's a lot more than just getting the right final number. It's about mathematically proving your underlying logic. Moving right along to Section 2, the methodology, which is all about systematic processing. You can think of this as the strict, standardized sequence you absolutely need to unlock your marks. Every single time you face a 3.8 problem, I want you to follow this exact order. Step 1, deconstruct the question. Step 2, extract the relevant data. Step 3, select your analytical framework, which in this case means separating the variables correctly. Step 4, execute your analysis with crystal clear notation. And finally, Step 5, present your results using the proper mathematical terminology. Seriously, if you memorize the sequence, you'll never freeze up staring at a blank page ever again. Next up is Section 3, the method mark strategy. This is your ultimate exam safety net. So let's talk about a massive source of math anxiety. What on earth happens if you make a tiny calculation error right at the very end of a problem? Well, the crucial thing to remember here is that examiners reward your systematic process. Method marks can and literally will save your overall grade. If you just guess or write down a completely incorrect final answer with no working, you get a big fat 0. But if you document your step-by-step working, if you show them exactly how you integrated both sides and of course added your plus C, you are going to pick up partial method marks along the way. Your working essentially proves your conceptual logic was sound, even if you accidentally dropped a negative sign at the very last second. All right, let's pivot to Section 4, Top Examiner Warnings. Consider this an autopsy of past mistakes. We're going to count down the top 3 errors straight from principal examiner reports. Here is mistake number 1. Time and time again, examiners report that candidates consistently throw away marks because they fundamentally confuse cause and effect. It happens all the time. When you're separating terms, you absolutely must correctly identify your independent and dependent variables. Think about it. If you put time on the wrong side of the equation, your differential equation is suddenly modeling the exact opposite of reality. And at that point, no amount of flawless algebra is going to save you. So always take a breath and ask yourself, which variable is actually driving the change here? Moving on to the second most frequent trap. Interestingly, this one has less to do with the numbers themselves and much more to do with your presentation. You are expected to follow strict conventions. Cambridge demands a professional level of communication. If your XDX and DY terms are just scribbled randomly all over the page, or if your integration signs are barely legible, you are going to bleed marks. Presentation is not just about making things look pretty. It's about proving your logical clarity to the examiner who is grading your paper. And that brings us to the third major examiner warning, which happens right at the finish line. Let me be clear. A mathematically correct answer is entirely useless if it defies the real-world logic of the scenario you're working on. If you're modeling, say, a biological population growing or a liquid cooling down, your final equation needs to actually make logical sense. You always have to check your final answer against reality.
If you run the numbers and calculate a negative time or a population of -5 rabbits, well, something is obviously wrong. You need to catch that before the examiner does.
Which leads us perfectly into Section 5, the final evaluation. Deconstruct, solve, and evaluate. So to achieve those elusive top marks, you've got to be able to translate raw data into logical, evidence-based conclusions. If a question gives you a text scenario, you need to extract the proportionalities of the variables so you can build your differential equation. Or if you're looking at a complex data table, you need to be hunting for those limiting values to help identify your core mathematical assumptions. It's a continuous cycle. Extract the relationships and justify your conclusions.
And evaluative thinking really just means you don't blindly accept a number. You actively question it. Ask yourself, what are the limitations here? What are the assumptions? When you find that constant of integration, you should be wondering, does this model assume a perfectly constant temperature? Does it ignore air resistance altogether? The top candidates, the ones getting the highest grades, are the ones who articulate these limitations clearly on the page.
Now here's a fantastic memory hack to help you keep all of this straight during a stressful exam. Try creating your own mnemonic, using the first letters of key terms for that deconstruct, solve, evaluate cycle. Finding a personalized, goofy phrase acts as a lightning-fast mental trigger. It completely bypasses exam anxiety and instantly boots up your analytical framework the very second you spot a differential equations question on the paper. So there you have it. By shifting your focus away from the paralyzing fear of getting a wrong final answer and instead mastering this analytical process, you completely unlock the path to top marks. Remember the golden rules. Identify cause and effect. Show every single step of your working out, and always evaluate your final answer in its real-world context. My challenge to you, grab a 9709 past paper right now and test this out. How many method marks can you capture today? Keep questioning, keep practicing, and I will see you in the next explainer.